Yo. So I went to the sound guy. I was like, why are we not having like world wrestling intro music for every speaker? Like, I should be able to come on stage in my outfit, like body slam somebody in the front row. Oh, dude. Next year, right, Dave? Next year. Dave was worried about hurting people. And I was like, it's fine. It's fake. They'll be okay afterwards. He was like, that's not true. They'll be in therapy for years afterwards. I was like, that's probably accurate. All right. So you guys are probably really sleepy. And that's important because this talk will definitely finish the job for you. I was dry running this again because I'm really afraid of Dave's negative feedback. Before I got here, and I was like 30 minutes into it, I was like, fuck, this is so long. I feel bad for the audience. So in order to make it more enjoyable, like I dug back into my my graphic design background and just have a bunch of really solid diagrams with pictures and lines and dots and drop shadows. So hopefully it is visually stimulating. So my name is Benjamin Watson, and on the internet I go by Rot Logics. It's not Root Logics, it's actually Rot Logics because it stands for my general rotten logic throughout life. Pretty self-deprecating. I'm the director of security research at a small consulting shop out of Atlanta, Georgia called Verisprite Security. Been doing Android for a while now. I was actually talking to Baz last night or yesterday, and it dawned on me how long I've been looking at phones. And yeah, that's pretty much where I've spent the last solid 7 years of my life, and I'm going to be presenting on stuff that I'm pretty proud of and I think is really interesting, and hope you also find it interesting yourselves. So, our agenda today: general inspiration and overview. I'll talk about why I even decided to dive into this research. We'll go over Android KitKat JIT internals of abuse, Android Nougat JIT internals and abuse. I'm going to talk about Oreo. I'm going to talk about Android P. And I'm actually going to shit on all this research later and tell you guys there are way easier to accomplish the thing I tried to accomplish via JIT. I'll talk about future challenges, like where I think Android is going, how maybe some of the things that they have decided to do prevent some of the things that I'm going to demonstrate, and we'll wrap up with a conclusion, and hopefully there's some time for questions if you guys care enough to ask. So it dawned on me that the title of this talk was somewhat misleading. I potentially am the only talk that's not actually going to be covering anything VR related or exploit development related. This is entirely post-exploitation and technique based. So I decided to call it that instead. Making Android malware great the first time. So, on the shoulders of giants, there have been people before me. Like most research, nothing is done in a vacuum, I would like to say. There's a lot of predicate knowledge. And for me, there was definitely a lot of predicate knowledge. Matthew Graeber and Ryan Wincy have both talked about this technique on .NET and Java. Matt discovered a technique where you could execute shellcode in .NET using the MSIL-based JIT overwrite. There's a CPBLK opcode, which is effectively the MSIL equivalent for memcopy, and he demonstrates in this really solid blog how to actually use this to overwrite a JITted .NET method to execute shellcode directly from memory. Ryan Wincy also talked, coincidentally, I think it was back in 2013, about the ability to actually use the unsafe API in Java to overwrite a JITted Java method with shellcode. That slide share is pretty sparse, but there are a few different references of the Java Oracle implementation of this in code out there. So if you guys are interested in looking at all the previous research, I'd highly recommend dropping into Google and going and finding all that stuff. So among other things, after absorbing all this research, I was really interested in whether or not this was possible on Android. Also, at the time, the stuff I was working on was, I feel like there's a lot of stuff we've been doing on Linux and Windows for a very long time. Advanced capabilities, stuff in memory, things we've seen time and time again. From my perspective, I've yet to really see that on Android. So not only was I interested in this, because my whole goal at the time was how do I do stuff entirely in memory without disk presence, but I was also interested in general, can we take anything that's been done in Windows and Linux, and can that be applied to stuff on Android? And so thus, almost 2 years of research. So the techniques I'm going to discuss today are entirely post-exploitation in nature. Here's our setup. So we either have installed a malicious application, malware or whatever, or we've got some type of arbitrary code execution in Java. The guys at MWR Labs actually already demonstrated what this would look like. The vulnerable git entry function, directory traversal via zip extraction, maybe you overwrite a jar, maybe you overwrite a dex. Now you've got code execution in Java. Our goal here is through that context, we want to execute shellcode entirely in memory through Java without loading additional shared libraries or utilizing JIT. So that means that this entire strategy is self-encapsulated into the thing that you overwrite. It's done entirely in Java, and it's not using any other shared object or shared library on disk, which means effectively, like, if you pop something via man in the middle, you would actually have maybe potentially like 0 disk presence. I don't know. So this means that a single application can have a self-contained solution for loading shellcode from memory into memory. My technique pretty much says that the only thing you legitimately need access to is just a virtual machine, or i.e. the Android runtime, and nothing more. This technique demonstrates the fact that after your initial access vector, you have 0 disk presence because we are not dropping anything to disk. From a native perspective, everything is self-contained. So I actually got this idea from Dave. He was like, so I have this ad network. I've installed a malicious application, and maybe I've got shellcode running in a PNG, and I download that PNG, extract the shellcode, and then load it into memory. And I was like, exactly, Dave. That's exactly what it is like. So I decided to try to visualize that. This is just an example, but the whole technique here is, download the PNG. We can extract the shellcode directly from the PNG, and then use the JIT technique to actually take that shellcode and then execute it in memory. So the JIT technique specifically is going to allow us to execute like our own native shellcode, or whatever that means for you. That could be an actual program that you run. That could be another dropper that could load additional things. The whole point here is that we are no longer executing code inside of Java, but we're actually executing stuff just within the process itself without the virtual machine. So the existence of a JIT compiler is not in every major version of Android. Up until KitKat, Android utilized the Dalvik virtual machine, which I think most of you are potentially familiar with, which was a JIT-based virtual machine. And then Android runtime was actually introduced in Lollipop, and then that replaced the Dalvik VM. That replaced the Dalvik runtime, so to speak. And the Android runtime itself is now ahead of time compilation. But when Android Nougat came onto the scene, it introduced a new JIT compiler, and the sole purpose of that JIT compiler is just to support the overall performance of an application running in the Android runtime. I'll talk about it later, but there's actually like an entire page where Google breaks down the whole like compiler workflow of how profiling works, the separation between JIT and ahead-of-time compilation, when a method is actually selected, and how that actually corresponds to overall performance improvements, if you're interested. Obligatory Android market share thing. I still find it hilarious that KitKat still has like 12% of the market. And then you can see here just the overall adoption rate. So from a target perspective, KitKat's still got 12%. Nougat is still low. Marshmallow seems to be dominant. And after I talk about all the JIT stuff, I'm going to talk about a technique that I developed from the JIT stuff that actually works on Lollipop all the way up through P. So in this research specifically, I just cared about KitKat and Nougat. I actually cared about KitKat first, and this was before I knew that Android Nougat even implemented or had a JIT compiler. So all the research that you will see today, it's pretty much a deep dive of both Dalvik's JIT implementation and Nougat's JIT implementation, or its JIT compiler. Again, to reiterate, our main goal here, execute shellcode from memory directly into memory. There were a few other devices used during the entire research process, but predominantly, I spent most of my time on an Nexus 5 running 444 and Nexus 5X running 711. So let's jump into a little bit of Dalvik JIT internals. So in order to understand a little bit about Dalvik's JIT internals, first we just need to answer the question, how does a Dalvik method or an encoded method, it's byte conform, become just-in-time compiled? Now, forewarning, at this point I don't really care about the why. For this research, I cared about the how. So if you ask me any questions about like performance, optimization, and stuff like that, I can answer maybe a few questions for you, but that information is less ready and available to me than really about the how of the thing. Super high-level diagram, Java source code, compile down to Java bytecode, compile down to Dalvik bytecode, and then that gets translated into or compiled into a Dalvik executable, and then gets loaded, allocated, linked inside of the Dalvik VM, and then that's where everything is executed. So abstracting a ton of stuff, I'm just going to start in something I'll call put in work. When a Dalvik method has been selected for JIT compilation, the compiler spins up. Once the JIT compiler has finished its compilation operations for the targeted Dalvik method, it calls a function called dvm JIT set code address. The compiler passes the target Dalvik method's bytecode pointer and the JIT translated code address as arguments to this function. You can see here in the implementation, the first two arguments, we have Dalvik PC and the native PC. Commonly within the virtual machine's code, you'll always see like a pointer to a Dalvik method's bytecode be referred to as DPC. So if I say DPC in the talk, that's what I'm referring to. But this is basically like one of the first entry points into adding and maintaining the overall state of JIT code. DVM JIT set code address is then responsible for passing the pointer to the Dalvik's method bytecode to a function called lookup and add. Lookup and add handles what I affectionately call lookup and add JIT operations. Here in the method implementation, you can see here also that the first argument is that DPC value. Lookup and add is responsible for finding available JIT entry slots in the JIT table. So both of these things are, they conform to two different structures within the virtual machine. The JIT table is the pJIT entry hash table structure, and this contains one or more JIT entry structures. The JIT entry, what we really care about, contains a pointer to the Dalvik method's bytecode and a pointer to its translated JIT code. So a basic breakdown of what the lookup and add operation goes through. So after JIT code has been compiled, the VM goes through and it looks for an available JIT entry slot within that JIT entry hash table, and then it is updated with the hash of the target pointer to the Dalvik method bytecode. The JIT entry is populated with the code address for that target Dalvik method. The translated address member is thus initialized, and then the pointer to the JIT entry structure is then returned. So within the DVM set code address function, the actual translated address, here highlighted in red, is then used to fill out the JIT entry's code address member. So now we have this JIT table, and inside of that we have multiple entries of this JIT entry structure, and it contains two fields, which are a pointer to the Dalvik method itself, and then a pointer to its translated JIT address. So the pJIT entry table structure itself is a member of a much larger global structure within the virtual machine called DVM JIT globals, which is defined as GDVM JIT. The JIT entry structure itself is comprised of a few different things, including the JIT entry info union and the JIT entry info structure. For this research, we don't necessarily care about the union or the entry info structure. Again, the only thing that we care about is this JIT entry structure because of the two fields that it contains, which is the pointer to the method itself and then the actual JIT address. So the way that Dalvik handles the actual JIT code itself is it's just memory mapped, and it's typically under the name Dalvik JIT code cache. And a pointer to the beginning of that memory map is stored within the GDVM JIT global structures code cache member. So at any time you ever want to know, like, you could technically parse this global structure, find the code cache member, and find the a pointer to the Dalvik JIT code cache if you didn't write like a proc pidmaps parser. So every time a method is translated, that JIT code pointer is stored within the JIT entry, is stored just somewhere within the JIT code cache itself. There are there are things like maybe if you're actually trying to write exploits for Android in this way, where you're going to utilize the JIT code cache, there would be like inline stuff that you would care about, and there's a linear way that they do allocations for the actual code pointers themselves, but you'll see why I didn't really even care about the JIT code cache itself, because I don't have to. So there are a lot of moving parts within the Dalvik VM, but specifically we only really care about like what happens when the JIT code gets executed from the interpreter's perspective. And the entry point, for the most part, into the interpreter directly is through this function that I'm calling DVM interpreter standard run. So this is really interesting. This function is actually implemented entirely in assembly. I did not know until I started researching DVM internals that the interpreter itself is almost entirely in assembly, which I just kind of fanboyed out, and I was like, that's fucking awesome. So this function specifically is responsible for loading the current program counter and executing it. If that method is JITted, then the PC will be pointing to the translated code within this thread structure that is passed as an argument to the function. And then the way that the DVM interpreter standard run actually exits and then re-enters the virtual machine's interpreter itself is there's a bunch of like global entry points as callbacks, and depending on like the context of the thing that's being executed, it can branch to one of those callbacks and basically re-enter the interpreter from like the JIT code that it's been executing. I don't know why, but I just love this picture. Is there anybody under 20 that's watched Back to the Future? It's phenomenal and sad. Yeah, so hopefully from the trained eye, my goal here is pretty clear. I don't care about the JIT code cache. JIT code cache is read executable. The only time that the JIT code cache is writable is during the compilation process. Whenever something's added, it's read-protected writable, it's added, then it's read-protected back to read executable private. However, I don't really care about the JIT code cache, at least for my perspective. I just care about the ability to attack things that I know I can control. In this case, I know that I can control JIT entries within the actual JIT table itself, which is going to be kind of my target for maybe launching my own shellcode. So I remember working on this research, and I was working with a senior guy at the company I was at, and there's a bunch of challenges. I got really discouraged early on just because my understanding of like Java and how to do stuff, especially with unsafe, I was like, dude, this is not looking plausible at all. And one of the things I was trying to find was just ways to actually read, write, and map memory from Java. From my knowledge about Oracle, I was like, okay, let's use the unsafe API. At the time at KitKat, the unsafe API is really restricted. They actually don't include a lot of stuff that Hotspot includes in terms of overall functionality. So I did have different primitives for being able to like read data. I ended up implementing some crazy garbage collective, like heap massaging shit just so that I could use unsafe to leak certain pointers back to myself from objects in the heap. And that just was really cumbersome. But after digging through the Android internals, I stumbled upon the libcore package. I was going to say right now, like if you guys can't see it yet, man, there's so much code that Android is just like explicitly stolen from Oracle. It is absolutely hilarious. I believe that libcore is one of those things. So I was very surprised when I started looking through libcore that libcore has a libcore.io POSIX class. And this POSIX class implements the libcore.io OS interface, which implements the mmap and mummap functions. I started looking into that, and I found that basically like libcore.io POSIX is just a wrapper around like a whole bunch of POSIX functions and their JNI counterparts. So, and from this perspective, we can access all of this stuff via reflection. So I literally just found, I don't know, just dicking around, like looking through source, and now I have a mechanism for mapping rewrite executable shellcode via this wonderful private API they provided.
Not yet. Not yet.
I also discovered within libcore, mind you, like this stuff, like libcore is a thing, but I didn't know that it was necessarily in Android, and you can find it originally as like a package provided in Java. So I mean, it's not anything new. They just included it within framework code, and you know, ended up being a solid choice for trying to achieve the things I wanted to do. So the libcore.io memory and libcore.io memory block classes, they actually provide methods for reading and writing to memory. And it's like, you know, peek something, poke something. So it can be an integer, long, float, byte array, char, string, etc. For the implementation that we ended up writing, we just used peekint, pokeint, and poke byte array specifically, which allowed us to read and write memory directly from Java within the virtual machine, and then also read and write the actual shellcode that we were mapping.
Thank you.
And this is what it looks like. It's pretty simple. The overall API utilization in general is like you pass it a long that's supposed to represent an address. It wraps it up, and then it gives you these nice functions. So poke byte, you know, from the address that you're at, specify an offset and a value, writes it to memory. Poke byte array, poke char array. Also, you know, the equivalents for reading peek would be the same type of implementation. So the JIT code cache isn't writable, but like I said before, that doesn't matter at all. We're not going to attack the JIT code cache because we can now use our read and write primitives for controlling the entries that are within the JIT table, and that is globally allocated data. So from the process, we can just, you know, read and write directly to it. In order to do this, we had to figure out where the GDVM JIT global structure was in memory. Fortunately for us, there's actually a simple reference to it, so we just wrote a basic process map parser, got the base address of libdvm, calculated the offset, and then, you know, we're good to go. So we started digging into the DVM JIT global structure itself, and the first thing that we saw or ran into was this table lock member, and specifically in the actual comments it says that it guards writes to the DPC and the translated code address within the actual JIT hash table. And so that actually got me worried because, you know, in Android, you can be executing in the UI thread, or you could be executing in a service that creates a new thread, if you guys are familiar with that. So, you know, depending on where we actually got entry, I was really concerned that, like, maybe if we're in like a really UI intensive app, that it was just going to be jitting all over the place, and the compiler or whatever was going to be holding this mutex, and if we try to fuck with it, then it was just going to crash. And so we're like, all right, well, maybe we just try to do the actual natural programming thing here and just acquire the lock ourselves. So we deal with it, and we deal with it with stability and reliability in mind, where we don't actually crash the, you know, the app that we're in or our app that we've put down. So we actually attempted to honor the table lock and whether or not it was being held by checking the pthread mutex t structure state member, and we were able to do this because we have those read and write primitives from libcore. If the table lock was not held, then we would acquire the lock by setting the state to locked in Java. However, we found that every time we actually pinged that member, the table lock was rarely held. And I actually thought at the time, I was like, well, fuck it, like, let's just race against the JIT compiler, and I was like, just for the sake of the proof of concept, like, maybe we can actually get lucky if we're just constantly trying to race. We found out that that wasn't even necessary, and I don't know if this is just a thing. Like, we had an entire implementation that we injected into Chrome, and even in Chrome, we just found that that table lock was rarely held. So at that point, I mean, we have an actual, we have like one iteration of this where we acquire the lock and we do it naturally, but we found that we never really had to, so we just moved on and didn't worry about it again. So attacking the JIT entry table itself requires overriding the code address field of a JIT entry for a given method or a partial method. So some things I do know about the actual JIT process. A JIT entry can either contain like an entire compiled method or a partial, like a basic block of an entire method. And unfortunately, it was really hard for us to determine whether or not this was like an entire method or a partial method. I think there's actually metadata within the JIT table itself or the JIT entry that'll let you know that. But for the most part, we just care about attacking the code address specifically. In Kickout, we were unsuccessful with being able to force a method to JIT in a consistent way. We tried so many different iterations of this. Sometimes it would work, sometimes it didn't. This is also probably because I was lazy and I didn't actually figured out any of the profiling or JIT optimization pieces. So there was a lot of rage quits in there. And I felt bad because I had an intern, so I just blamed it on the intern, like, it was his fucking fault. I'm the god in this situation. Why aren't you writing good code? He's still my intern, by the way, too. He's a glutton for punishment. And actually, he worked on a lot of this stuff with me, and I'll give him a shout out at the end. So because we were unsuccessful, we decided to attack the entire JIT entry table for all populated entries. So in order to attack a specific JIT entry, we first need to understand which classes have already been loaded within the virtual machine. And for each method that's extracted from a given loaded class, we need to determine if the pointer to that method's Dalvik program counter or bytecode matches the same Dalvik PC within the JIT entry itself. And the only reason why we would do that is because we're actually trying to be really targeted. Like, I know this method, I'm gonna call this method. Outside of that, we have another implementation where we JIT spray the entire JIT table with corrupted JIT entries, and once we get code execution, we wrote some really painful shellcode to actually like repopulate all the JIT entries so we can restore context and nothing crashes. So understanding which classes are loaded it's really simple too. There's a hash table that contains all of those within the overall VM global structure for an application. And for each class, it conforms to like a class object structure. Each class has a vtable, and inside those vtables are basically all the virtual methods for that given class, and those conform to the C method structure. And the C method structure is how an actual method is represented within the virtual machine. So like you write foo, well there's the method structure that's representing that in C from Java. So the method and structure itself contains the instruction field, and this points to the method's Dalvik bytecode. So basically, if we know that a method's been JITted, i.e. there's a translated code address there, and that DPC field in the entry matches the DPC field within a method that we can extract, the instruction field that we can extract from a loaded class, like now we know that that's a method we can target. Something I actually don't even point out here, what's really nice is in the method structure, they have a name, like a constant char star name field. So you can literally like, oh, that works, go back up, get the name, and then you can use reflection to call it. So a basic strategy here. In Java, we're gonna mmap memory and write our shellcode to our allocation. Obviously, we're making it executable. Through libcore, we can access the shellcode's base address. So if we're targeting one or we're targeting a bunch, We save off the original JIT entry structure in order to restore it later. Then we use the pointer to our shellcode, and we replace the code address within the target JIT entry itself. So our shellcode went through a few different revisions, but for the most part, this is kind of like the high-level implementation of it. The segment itself contains a basic stack and a basic text section. So each section itself is referenced via labels and PC relative addressing within ARM32. The stack holds all execution context, including arguments and whatnot. And the way that we prep the stack segment is we actually fill out all of the data in Java. So we write all the context, specific information, and arguments in Java. And then the way that our shellcode works is it understands that like this is the stack and uses PC relative addressing to actually adjust the stack frame and then pull off arguments that we've already prepped in Java. At a high level, the text section is responsible for immediately reverting all changes to the JIT entry table. So this could be one JIT entry itself or multiple JIT entries. And basically what that means is that we're going to go and repopulate all the original data. In some cases, like I've said before, we may have just taken the spray everything approach. So we have to actually go and repopulate all the JIT entries that we've modified, because if we don't, then there's a high chance, I mean, our shell will just be executed infinitely. But, you know, from a reliability perspective, we want to make sure the user doesn't know that anything has happened and everything kind of goes on as planned. It also makes room for a bunch of, so we actually make room for a function called stack frame. The overall implementation for this is we just call system to invoke the log command. And then from there, we go and we clean up and restore execution context. From the actual point that we gain code execution, like that context specifically, we had to go and restore all the original code addresses to the JIT entry or the JIT entries that we've modified. From initial foothold, we control R0 and R1, and R0 and R1 should be pointing to the actual original code address. So we restore register state in that way, and then we branch to the original code address. And then the way that we have all the cleanup routines, like after the original code address is executed, it just calls its re-entry point into the interpreter, and then we're good to go, and then nothing crashes. So our strategy for this was basically to target all the UI-related framework methods. We observed when we were tracing everything, like over months, that it appeared that, at least in KitKat, the methods that were getting JITted the most were things that were UI-related. So in order to be specific, we just wrote like another process maps parser. We identified all the target ranges for framework code and then validated that within the framework code, obviously that's where you're gonna have like activities, fragments and stuff, where we saw we're getting, those methods specifically were getting generated. So to summarize, if we have a JIT entry with a DPC value that points into this range, basically kind of doing what I've already talked about in order to validate a specific JIT method. We look at that method, we validate that it matches, we hijack the code address, and then we execute that method directly. In this demo, this is basically like the spray and pray thing, where we go through, and we're not targeting one specifically, but we go look at every single JIT entry. We find one that was in framework code, we hijack the code address, that executes our shell code, and then from there we would go back and clean up and restore. Play. Okay. So we're doing a lot of the prep work, a lot of the proc map scanning. You can see here that we're getting symbol addresses, we're parsing the loaded classes. We find the actual entry table itself. Acquire the mutex. And then we start spraying. Okay, so we've gone through and we've done a whole bunch of modifications. In the range, that's the framework code. We've already done our patch out here. I wish our logs were a lot better, But effectively, we've hijacked every single JIT entry that has framework UI related code. One of those things gets called. Our shellcode is then responsible once one of those methods gets called to execute system and then pass a login command. You can see here, these violent delights have violent ends. And then our code goes back, whatever that JIT entry is that gets executed, that shellcode is still responsible for going in, repopulating all the modified JIT entries, and then restoring regular execution context. So now we've effectively used and abused the JIT to execute shellcode directly from memory. We haven't loaded any libraries, and then we restored context. So yeah. NuGet JIT internals. So a JIT compiler was added in NuGet in order to improve performance. Like I said, Android maintains a JIT workflow of the JIT compiler, as well as overall visualizations of when it's used, how it supports AOT. I would say the JIT compilation process itself is relatively different, but some of the stuff is the same. So a Java method is represented as an art method C++ class in the Android runtime. And within the art method itself, there's a pointer to something called entry point from quick compile code. Now, this can point directly into the interpreter, or it can point to other different locations depending on the functionality of that method. However, it should be pointing at JITted code if that method was actually JITted itself. So when a method is JITted, the JIT code is stored as an entry point within the JIT code cache. This is pretty much the same as in KitKat. And that JIT code cache maintains read executable permissions. When new JIT code is added, the commit code internal virtual function from the JIT code cache class is called to actually add the translated address into the map, into the actual cache or the memory map itself. And there is an internal state map within the runtime that actually controls the pairing between an art method and the JIT code. And it would maybe some would assume that I would just be able to attack this, and actually it becomes a lot easier than that from an implementation's perspective. And there's a ton of code in the Android runtime, but for the most part, internally, when a method has been, basically the operations have completed, there's some internal instrumentation that happens where the quick code from the entry point for quick compile code or whatever is pointed to the translated JIT code or the translated JIT code itself. So for NuGet, our plan of attack is basically force JIT a target method that we can control, find that target method's art method object in memory, and then overwrite that art method's entry point with a pointer to our shellcode, and then we can invoke the JIT method via Java, either a direct control from an instance object or via reflection. So for some reason, I don't know, maybe it's because JIT compiler is better in NuGet, but getting a method to JIT reliably worked really well. We still, to this day, have all of our read-write primitives from Java through libcore. The problem that I ran into is that it's difficult to leak an exact art method address for a given Java method. And remember, we're not using shared libraries here, trying to do this entirely from Java. Because it is really difficult prior to Oreo, you can still achieve the same thing. You just have to scan the memory map where all of the art methods are allocated in order to find your target method. You could also scan art methods and just hijack each entry point if you validated that it's in the JIT code cache, but in some instances you want to be really targeted. So finding a JIT art method is pretty simple. There's literally one or two memory maps where all that code is stored. And then the quick compile code address within the art method itself. If it's been JITted, then it's going to be pointing into the JIT code cache. Now, figuring out if the scan art method is the target art method proved to be really difficult because the C++ class itself does not have either an inherited member or a member that actually references the name of the method itself. So it's not like, oh, that's foobar, that's just art method, until I can figure out what it actually is. So the art method C++ object itself, or its class, contains the dex method index member, which is the method ID's index for itself and its associated dex file. So you can go through and actually parse the dex file in memory and then look for that associated index, and from there you can reference the name of the method if you want to get really targeted. So it's easy to validate it that way, or you can just do the spray and pray method. So once we found a target art method, we override it with we override that entry point with some shellcode, which we've already allocated in memory. And the strategy itself, well, the strategy is different. It's all ARM64. But the implementations are pretty much the same. Then we use reflection to invoke the method from Java. So I've gotten this question a lot. Why would you do this? Why does it matter? I'm constantly thinking about things from a post-exploitation perspective. And I'm not necessarily thinking about the current state of things. I'm thinking about maybe 5 or 10 years down the road. And again, my whole goal here is we do all this stuff on Windows. How do we do it on Android? So how do we utilize this actual technique to do anything valuable? Well, I saw this on Twitter, maybe it was a Gruck. If the disk is lava to you, you can write your own in-memory text loader, elf loader, or oat loader. Full disclosure, I've written both a dex loader and an elf loader using this technique. So dynamically load executable types from memory in memory without dropping into disk. Up until NuGet, like NuGet has an in-memory dex class loader, but from 4 to 6, there was nothing like that. So this technique actually allows you to utilize more in-memory loading without having any types of disk presence. For people that have been working in Android for a while, they are probably aware, but for everybody else, the runtime specifically gives you constructs for loading things into memory. So without having to load a library or utilize JNI, or Dan, you mentioned how much you hate the NDK. You don't have to do any of that. You could just write your in-memory loader and then write it really as position independent, and then have the technique execute that and do a whole bunch of other things. Completely abstract to anything else. If AV caught anything, maybe it would be useful. Of course, AV is not going to see this at all. And then maybe in 5 to 10 years, where the OEMs are like, fuck, maybe we should implement security managers because AV products are bullshit. Then we get to a point that this stuff actually potentially matters from a malware perspective. So basically, pull down your shellcode, load it in memory, execute it from memory. Your shellcode pulls down the DEX, loads it in memory, executes it in memory, and then you do other stuff. Persist, escalate, collect, all those kind of operations. So I'm literally about to tell you that none of that research matters anymore. Well, some of it does. So with the ability to write memory within the virtual machine, it is actually easier to take a method. So we don't have any libraries later, right? Let's just say you have one method. It's easier to actually convert that method into a quote-unquote JNI method than it is to attack the JIT. So if we have the ability to update the access flag for a given art method and tell the runtime that this is a JNI method, it will attempt to execute basically a member within that art method as that member is pointing to a location in a shared library. So once you actually convert a method into a JNI method, then you can replace the method's data pointer with your shellcode, and then you can just execute it. Because you've literally told the virtual machine or the runtime, you're like, this is a JNI method now. The pointer is in, somewhere in a shared library, just execute it. And for the most part, there is some validation and whatnot that I remember seeing, but for the most part, it just says, okay, cool, I'm gonna run it now. So now you don't actually have to JIT a method, you don't have to rely on JIT. All you need is to be able to look up a method, which is still difficult up until Oreo, modify it in memory, put some shellcode in place, replace the pointer, and then you can execute it from Java, and then you've got native execution. So it is still in Android Lollipop and Marshmallow and Nougat. You still, unless somebody goes out and like finds a really neat trick of leaking ART method addresses that I haven't found, that would be really solid. You would still have to go through and you have to scan all of memory in order to find allocated ART method for a given method that you're going to attack either through something else or through your own thing. Until Android Oreo stole a whole bunch of Java code from Oracle. So now the Java lang reflect method actually includes a member that is inherited from the executable class called art method. And guess what? If you reflect upon any Java method now in Oreo, you can get the address of that given method from Java. So now we don't have to search for anything in memory. We just ask the runtime to give us the address, and then you can use read-write primitives to go and modify that method, and then just execute from Java, and there you go. Effectively, you've escaped, quote unquote, the machine, virtual machine, and then you're just executing your thing. And I would actually like to point out, Zero Day Initiative just released like this Java type confusion thing with method handles. That is also in Android. They ended up taking and implementing that themselves. So not only can you use the Java lang reflect method, but you can actually use their implementation of a method handle to also get an address of an arbitrary Java method, from the runtime or from the VM. I used Frida a lot, especially early on. I wrote a pretty robust tool suite around Frida. For the most part, even though I had source, I still wanted to understand like a lot of the call flow intricacies about what was going on. So I wrote a lot of dynamic instrumentation on top of Frida. We ended up using Keystone for all of our assembler stuff. We hand-rolled ARM32 and ARM64-bit shellcode strategies, and then we used Keystone to assemble all that stuff. And I wrote a Python wrapper that would take the output of Keystone and then convert it to a Java byte array. And we just used like static byte arrays within our test applications. But obviously, you can just download some shellcode over the internet. It would be the same difference, but it was just easier from a testing perspective. Future challenges. So, and I had a discussion with somebody yesterday. I don't believe the things that Android is doing right now to be a security thing. I firmly believe that it is a stability thing among its developers or people writing applications and whatnot. So Android has begun to lock down private APIs with basically a special access flag that I believe is just encoded into the method when it's built. So the runtime, like it prevents you from accessing it via reflection. And what that looks like from my first glance at it is that when you try to invoke it, the runtime is like, hey, does this method have the access flag? Oh, this is private, go fuck yourself. So I don't know yet because they're not like scoping everything into the private API bit. Potentially libcore becomes scoped into this group, which could remove like all the really nice POSIX stuff that we use, like InMap. There is a way to de-restrict private APIs. However, at least for my first initial attempt at that, requires a native library. So unfortunately, it defeats the purpose for this kind of self-contained strategy. What a POSIX interface is removed entirely. We actually wrote a ROP implementation because we hate ourselves. So you still have access to things like direct buffers and direct byte buffers, which you can build an entire ROP stack within. And those classes actually will give you a reference to your allocated address. Initially, we thought we were going to be able to use that, but all that stuff is allocated on the heap, and obviously you don't have any like the ability to change permissions on that on the allocation, and it is definitely not a memory map. And over the years, Android has actually added a ton of more functionality to the unsafe API like it is more powerful than Oracle's implementation at this point. So even if they were like, fuck it, we're moving libcore, which I really don't know if they would be able to do at this point. There's a ton of stuff that relies on libcore from many different perspectives. We could technically now use the unsafe API because now it gives us really nice rewrite primitives. And from Oreo on, we have the ability to leak or get access to the art method pointer for a given Java method. So now we can just, potentially allocate a direct byte buffer, throw in our ROB stack, take a pointer to that, use the unsafe BI, hijack the entry point, or modify the art method, hijack its entry point, and then get code execution that way. Conclusion. So for both KitKat and NuGet, this research took a long time. It's probably because I'm dumb. Tooling was a pain in the ass. So it wasn't necessary, at the time it wasn't just like, oh, we escape and write shellcode, like, building stuff on top of that. And that made it a lot harder. And at the time, there was other stuff going on, and I felt like the JIT stuff was pretty stupid to even attempt. But it ended up working out, and it was a really great learning experience. And that's like one of the biggest things why I even attempt research at all. If I'm going to research anything, it's really predominantly something I have zero knowledge about, because why do anything unless you're going to learn and you're going to grow? And I definitely did a lot of that over the last 1.5 to 2 years, especially coming from a point where I thought I knew a lot about Android. I found out I didn't know shit about Android. Hopefully the research here that was the whole goal, right? I was just trying to demonstrate that some of the techniques that were demonstrated by Matt Graber and Ryan Wincy, and like there's still crazy shit that malware's doing in .NET. You can do all that stuff in Android. From my perspective, right, like why would you even care about doing this now? But again, it's not necessarily about like looking at the current landscape of where these phones are and where the operating system is or where our defenses are. It's looking into the landscape. I get really excited about offensive research. Whether or not anybody gives a shit about it, whether or not it's applicable right now, I still found this really fascinating. Yeah, special thanks to Varmint Overflow. I would go follow him. The kid's fucking 20 years old and just slays. I wish I was as smart as he was at his age. And then shout outs to a few homies for challenging me to be better and really pushing me forward over the last few years to not be and make cool stuff. There's my Twitter. There's my company's Twitter. Holler at me. I'll be around. Shit on my research. Let me body slam you. Let me body slam you? No. All right. Thanks, guys.
Otetaan kysymykset.
All right. Does anyone have any questions? Okay, we have one question right away.
Thank you, Daniel.
No.
So great work. I was kind of wondering, though, what the main advantage of being able to run Android native code was, since you already had access to Java. And from personal experience, I've dealt with a lot of managed implants before, so I was wondering kind of what the native execution would get you.
Well, the biggest thing was to just write in-memory loaders without actually having to put a library on disk. So some of the research was like, how do I write a DEX in-memory loader? And I wanted to write a DEX in-memory loader without having any other disk presence. So I was like, all right, well, the only way I can do that is I need to actually like have access to the Android runtime implemented in libart, this libart shared library. And there's a ton of functions I want to call in there, but outside of loading a shared library to do it, I wanted to figure out how to do that without even having a shared library at my disposal.
What functions did you want to call in the art library?
So there is, in Android itself, all the actual DEX class loading calls directly into the runtime. And there are a few different constructors that will actually load and link a DEX that's been memory mapped into the virtual machine. So you can have like a DEX, load it and get it linked in the virtual machine from the technique, and then go back to Java and just call it like you would call normal Java. So the whole point was to load it in memory from not having it on disk. without having another library to do so.
So let me see if I understand this. To actually load managed code from memory and run it, I'm assuming that's what Dex is. I'm not an Android guy.
Yep, correct.
But you needed to actually get native code execution and do all this to get that working.
Right, if I didn't want to have disk presence.
Okay. All right, that makes sense. Thank you.
Yeah, absolutely.
Yeah.